Hello, everybody. Good afternoon. Good morning, depending on where you are in the world. We have people still joining us at the moment, so if it's okay with you, I'll wait a minute or so just so that other people can get in, make a cup of tea, put their feet up, etc. So if it's okay with you, I'll see you in a few seconds. Okay. Good afternoon, everybody. My name is Mark Bunch, and welcome, first of all, to another of our webinars. This one is on quantitative risk assessment. As we've only got an hour or so, I can't go into too much detail, but I can certainly give you a flavour of what quantitative risk assessment entails and how you might engage somebody like us to go about it and the kind of things that we will tell you about quantitative risk assessment. So to make a start then, we have a sort of program to get through. So this will really be a basic knowledge surrounding QRA. So we're going to talk about how we develop the scenarios that we take forward to quantitative risk assessment, how we do the consequence and the likelihood assessment, and then what it means. It's the summation. It's putting this information into a format that can be readily used and put to good use, because as it stands, it's just a numerical exercise. Nothing changes until you make changes to the plant. So it's the reporting and the recommendations and the further risk reduction measures that are going to generate safer plant and safer processes. But I'm contractually obliged to tell you a little bit about Sigma before we start. Sigma is a company based out of Winchester in the south of England. I'm based in the northern office up in North Yorkshire, but we have offices in both India and in the United States now as well. And we have a consultancy service, which is engineering process safety management. QRA, yes, we do that as well. Hazard identification, PHAs, those kind of things. And we have a very well-equipped testing laboratory as well, which will tell you whether things are going to go bang, how big that bang is going to be, and how well you need to control your chemistry. And we provide training courses as well, and that can be online, it can be at your premises, bespoke courses or generic ones. We do all of that as well. The consultancy services, PSM I mentioned, fire and explosion hazards, process hazard analysis is in there, functional safety, we do that. Chemical reaction hazards, this one, the quantitative risk assessment, and provide training workshops as well. And the testing, we do things like combustibility studies, powder and fire and explosion properties of materials. You send us a sample and we'll tell you how bad it is. Gas and vapors, electrostatic properties as well. And we have facilities for doing chemical reaction testing as well. So there's no excuse now. You have to get in contact with us, do it all. Okay, so risk management and hazard identification. So let me preface everything by assuming that you know already that there is a difference between hazard and risk. Hazard is how bad it can be, the potential to cause harm either to people or to the environment, and risk is the combination of that together with frequency or the likelihood that something is going to go wrong, that harm is going to be realized in the form of losses. So that's it's kind of a prerequisite to everything that we're going to talk about, because it is quantitative risk assessment, and part of that is going to be evaluating how bad the hazard is going to be, the consequence of having a loss of containment. And part of it is going to be the estimation of the frequency that goes with that. That gives you an overall idea of risk, and it is the risk either by reducing the consequence or reducing the frequency with which you have a loss of containment that generates safer plants and ultimately makes our lives a lot easier. So with that in mind, there are two case studies that are particularly important with regard to QRA. The first is Flixborough. Oddly enough, we're just coming up to the 50th anniversary now, I notice, June the 1st, 1974. This was a loss of containment. There were many causes for it, in particular the lack of change control. But it could have been an awful lot worse, and this is where QRA comes in. What you can't see on the drawing is where, well, you can actually, it's the main office block, which is, you probably can't see the mouse, but I'm circling it now. If you can see where it says main office block in the left drawing, that would normally have been occupied by a large number of people. Now this explosion happened on a Saturday afternoon, and although it leveled the plant and did a substantial amount of damage and destroyed that main office block, the number of casualties was around the 54 mark. It would have been many times that, or potentially many times that, had it not happened on a Saturday afternoon. So having people located close to where there is the potential for a large fire, deflagration, toxic release is something that we need to be aware of so that we can locate these people properly. And of course, the other one for which the location of people working on plant is important was the Texas City disaster. This was 2005, an explosion and a fire. 15 people were killed and over 100, well, 180 is quoted there, were injured. The 15 people who died were in temporary accommodation, porta cabins, which was close to the isomerization unit, which is where the explosion occurred. Now, we don't tend to do that these days because we understand that putting people in harm's way is one of the easiest things to solve. We can get people out of harm's way a lot easier than we can change the process, for example. So QRA would have given us a good insight into how that might have been avoided in the first place. So we can use it for risk management. We can use it for guiding our decisions as to how to make things better. We can increase the awareness for hazards, and that leads into very, very good process safety management, like appropriate training for people. It helps with emergency response planning as well. If you know where people are going to be hurt or most likely to be hurt, and then we can plan our emergency response around that. It allows us to communicate our risk to the public as well. Whether you think that's a good idea or not is up to you, but it is a legal requirement, especially if you are operating at a coma site, where there is a duty on you to release information to the public as well. But if you're going to have off-site effects, and QRA will tell you whether that's likely to be the case or not, communication of risk to the public is a good idea. And it's also sometimes a duty under the regulations where you've got major accident hazard potential to do some form of QRA to demonstrate to yourselves, to your shareholders, to your customers and your suppliers and the people who are your neighbours that you are fulfilling your duties under the regulations and that you understand your hazards and your risks. In 2005, there was also the Buncefield explosion. And a couple of years later, after the court case, I remember on the news, the head of the Hazardous Installations Directorate being interviewed on the steps of the courthouse after the court case. And he was saying this sent a very clear message to industry that they need to answer 3 questions. Do we understand what can go wrong, i.e. the consequence, the hazard that you've got? Do you understand what your systems are for preventing it? The safeguards, the procedures, the people that you've got. And do you understand, do you have information to assure yourselves that you are managing those risks effectively, that those safeguards are working as they should? All of which is a demonstration to yourselves and to the regulator that you have got your risks under control. QRA is a part of that. So the process of risk management, first of all, what are we trying to achieve? What is the design intent? What is your process intended to do? And then the first of the questions from the regulator, what could go wrong? And we do that by typically some form of process hazard analysis, whether it's a hazard, a HAZOP, a checklist, or whatever your preferred methodology is, depending on how big your risks are. How likely it is and how big an impact is the risk analysis part. And how significant that is, and therefore what you need to do to reduce that risk is the risk assessment. It's a case of so what? Once you've done the risk analysis, risk of what, from what, and to what, and then that fourth what question is so what, and that's the risk assessment side. And therefore, what is the most cost-effective control or mitigation options available to you? And that's the risk management side, how you manage those risks and how you reduce them as a result of good management of those risks. So, as with all good policies and procedures, we have a little flowchart to help us do all of that. And this is the one that we would typically use for a QRA methodology. We'd set scope and do a site visit first of all. So there's a little bit of pre-work to do to define what the scope of the study is going to be, and then to visit the site and collect all the data that goes along with it. Things like hazardous properties of materials, the way that you're processing, the conditions of temperature, pressure, flow rate, and so on. And then we can go into a form of hazard identification study, which will generate the scenarios. If any of you have been in either a hazard or a HAZOP, you'll know that the way we generate scenarios is by these deviations from the design intent. And that gives us a number of potential scenarios along with their consequences. So the frequency and the consequence analysis are what we need to do next, because one is the hazard, the other is the frequency, and together those are what give you the risk. Because this is quantitative risk assessment, we put some numbers on that as well, and we'll talk a little bit about how we do that in the coming up slides. But by putting numbers against it, we have a numerical representation of risk, we have a numerical representation of consequence as well, and that means that we can be considerably more confident about the amount of harm that we're going to inflict potentially on people or on the environment by looking at the ranges to particular radiation levels or the ranges to particular concentrations if it were a toxic material. And together the consequence data, the frequency data, and therefore the risk data allows us to calculate two measures, well, a number of measures, but these are the two that we commonly refer to, the LSIR and the PLL. You'll find that process safety management is as full as three-letter acronyms and abbreviations as any other branch of the sciences. LSIR stands for the location-specific individual risk, and the PLL is the potential loss of life. Those are the measures by which we judge ourselves. That's the risk assessment side, the evaluation of that risk against criteria. I'll introduce you to the criteria that we use a little later on. Whether we meet those criteria or not then decides for us whether we need to take additional measures in order to reduce the risk further. Legally, at least in the UK, you're required to reduce the risk to as low as reasonably practicable and make a demonstration that it will be grossly disproportionate to make any further risk reduction in terms of the benefit that it gives you. But ultimately, we would like to remove as much of that residual risk as possible. We then write a final report which summarizes everything. There's your demonstration, and this becomes a living document then, because changes to your process, changes to your surroundings, all have an effect on the amount of risk on which you are imposing on other people. So there's a little flow chart. For hazard identification, I mentioned a few other tools there. They vary in terms of rigor, I suppose. That's probably the best way of putting it. If you've got a relatively benign process involving a lot of water and not much else, then things like checklists and brainstorming activities can work perfectly well. But if you've got a thoroughly integrated, an oil refinery or something, then something like hazard interoperability study would be the way to go. But there are lots of others as well. HAZID, if you've ever come across those, is like a HAZOP. It's sort of a HAZOP light. It still uses guide words and therefore it's quite rigorous all the same. But it's a little less resource intensive. But we have things in here as well, like failure mode and effects analysis, and fault trees and event trees, all sorts of techniques. Some more fun than others. It depends whether you do them with me or not, but yes. Now, I mentioned right at the outset on that we need to define a term, an extent of the study. Once we've got that, we sectionalize it. That's an awful word, but we divide it into sections or nodes or whatever it happens to be, your preferred nomenclature. But the idea is that if you can identify isolatable sections, what the inventory is likely to be, in particular if you go, for example, between ESD valves, you've got a fixed inventory that sits within there, and that allows us to generate the worst case consequence rather than just having a portion, if you like, released. It also aids in the standing of the process, so you're not faced with too many scenarios to model at any one time, and it means that every single element is given its own importance. And that's a very useful thing to do, having sections that are not too large that they become unwieldy, but not too small that they become unrealistic, or at least unrealistic to do in the time available to you. So we section our remit out into smaller sections. So as I mentioned, one ESD valve, for example, to another would be a good way of doing it. But pumps and compressors we don't usually consider as isolation. We imagine that stuff may bleed through. Control valves are used to control rather than provide set-off. So we don't usually consider those as isolations. And then we can go into talking a little bit about the consequence calculations themselves. This is at its most basic, I suppose, the application of mathematical formula to the consequences from toxic and flammable releases. There are various tools that you can use to do this. They don't differ greatly because the underlying mathematics that supports them is well understood and pretty sound these days. If you're looking at the release of material from an orifice, for example, you'll know that this will be influenced by things like internal pressure and therefore the flow rate out, the buoyancy, the temperature, and atmospheric conditions as well. Those are built into the model, and the way it works at its most high level is it's a normal distribution that's looked at with three axes. So an axis that runs in the same direction as the release direction, one at 90 degrees to it horizontally and one at 90 degrees to it vertically as well. And there are therefore three normal distributions that you could look at, one in each of those planes. And we use the mathematics using the pressure and the flow rate, etc., to determine how wide that normal distribution is, and then use things like the weather conditions to influence the shape of the normal distribution. We can distort it to one side or another, and that's done via manipulating the standard deviation from the normal distribution. If you didn't get all that, I don't blame you. I did actually once produce a spreadsheet that did exactly that, and it was one of the nicest pieces of work I've ever done. I don't think I could do it again, though. Fortunately, there are other tools to do it, and there are offerings from both the HSE and people like DNV producing consequence modelling software. So We need to model various discharge rates. We need to know the size and the shape of flammable and toxic gas clouds in order to be able to see what happens when that encounters a person, whether we ignite it or not. The consequence modeling software will also tell you the distances to various levels of radiation or to various concentrations if it were a toxic release, and also the distances to various overpressure values in the case of explosions. What I haven't found that it does at the moment is sudden releases of energy due to things like a pressure burst. For example, if you just popped a balloon, for example, the pressure burst associated with that is slightly different. But there are other tools and techniques for modelling that kind of event. So there are a number of consequence effects that we would look for. If we ignite things, we've got various forms of fire so that we can have a pool fire, a flash fire, or a jet fire. If we had a toxic relief, we can have just a concentration that proceeds downwind and has the potential to hurt people. And for explosions, we've got various types here as well. We've got a BLEVE, or a boiling liquid expanding vapor explosion, vapor cloud explosion, or indeed a detonation. And the reason that we never used to consider detonations as being terribly likely to happen, but since Buncefield, which proceeded to detonation, we now include that as well, known as a Buncefield type incident now. But it essentially means that it's not just a combustion reaction that's going on. The molecules are physically being banged into one another by a propagating shockwave by virtue of having containment in the area and congested plant, which tends to accelerate the flame as it goes around the obstacles. So those are the various effects that we can have. For jet fires, let's have a quick look at those. Occurs where gas is atomized, or an atomized liquid is ignited close to the source of release, and you end up with a jet flame as a result. The amount of damage that it can cause depends where you are, essentially, because they are pretty directional, as you might expect. The length of the flame and the direction being the principal things that you would want to know, but also the temperatures that you could get up to, the radiation levels that you would generate from these events. Typically, they can burn very, very hot indeed. Pool fires. A flammable liquid forms pool, which then ignites. Again, it's the thermal effects. We generally assume that people have a pretty good chance, unless they're actually caught in the pool, then it's much easier to walk away from a pool fire. If it's a running pool fire, they don't tend to go that fast, although they can, of course. Flash fires, a flammable cloud released, it doesn't ignite initially, but finds a source of ignition subsequently and then flashes back to the source. That we would call a flash fire. It's slightly different, it's less violent, but very hot, less violent than a vapor cloud explosion, which is the next one, where we have a little bit of confinement. In order to have an explosion, you need something for the combustion gases to react against in order to generate pressure. The flame front tends to accelerate, and if it's unconfined or has less confinement, it accelerates to less than the speed of sound. If it accelerates to greater than the speed of sound, as is the case with gases like hydrogen or ethylene, and those can proceed to detonation quite well, which is why you tend to get more of a bang with those. As well as the radiation effects, you've got the consequence of arising from the overpressure that's generated by the explosion, this accelerating flame. A BLEVE, if you've come across these, no doubt you've seen the videos on YouTube of boiling liquid expanding vapor explosions. Essentially, you've got something that wants to be a gas restrained by, for example, a vessel, and that vessel goes, and everything that wanted to be gas suddenly finds its opportunity to become gas. If it's flammable as well, then you can end up with a very, very violent explosion, but you don't need it to be flammable, because you've got the vaporization and the change in volume that's also associated with that change in pressure. So as it vaporizes, it generates the consequence at the same time. They are extremely violent explosions. So if you haven't seen the videos on YouTube of a bloody, go and check those out. So the modelling will give you the distances to various radiation levels as a result of the consequences that I've just described. Other things that we need to take into account are built in to a lot of the modelling software as well. And these are things like the atmospheric stability. We have two considerations to look at. One is thermal turbulence, which is just the natural heating and cooling cycle of the land mass in the atmosphere. And then there's the mechanical turbulence, which is generated by the wind speed. And this is a tricky one, because it can lead to counterintuitive effects. If you think about a release from, for example, a release from a relief valve, which is up at high level and perhaps angled away from the vertical by about 45 degrees. If you had a very fast release, a high velocity, a high volumetric flow rate through there, you might expect the cloud to go further, because you'd be considering things like momentum of the cloud, and you'd be right in that respect. However, there are other things that influence that, and as you have a higher speed exiting the tailpipe, as it were, you can also get a higher entrainment of air, which tends to dilute that cloud a little faster than it might otherwise have been. So you can end up with almost counterintuitive concentrations downwind of the release. So modelling is important to do in that respect, because you wouldn't necessarily know that any other way than if you actually applied the mathematics to it. So it's worth bearing in mind. And we generally model according to something called the Pascal Stability Scale. For the UK, we use 2F and 5D an awful lot. 2 refers to the wind speed, so 2 meters per second and 5 meters per second. And the letters are there to tell you whether it's day or night and how much sunlight you're getting. So 2F is a clear light wind night, and 5D is a little bit breezier, could be in the day, could be at night, doesn't matter. But those two have an effect on the normal distribution that I mentioned earlier. So they can move the cloud further downwind than you otherwise might have expected, or to one side, or increase or decrease buoyancy as a result as well. So it's important to know where you stand and do at least a couple of different weather types when looking at the QRA. Okay, that's what I said. Yeah, that makes sense. Event trees are very useful. Depending on the type of release, we can build this into the model as well and do a frequency analysis on what is the most likely impact of having the loss of containment. So if we look at the top one, which is the continuous release, if we ignite it immediately, we'll end up with something like a jet fire. If we don't ignite it immediately, and we ignite it after a period of time, we can end up with a vapor cloud explosion. Or if we don't ignite it at all, it's not so much of a problem, but then we'd have to look at the toxic properties of the gas. And for an instantaneous release, it's a similar sort of exercise. Whether it's more likely or less likely to be any one of these is going to be down to the material properties, your judgment, whether there is a hard source of ignition nearby, or whether you've got good desire. You've had somebody like Sigma come in and do your desire risk assessment. You haven't put any flares nearby, and the smoking shelter isn't nearby either. So that'll be very much down to the way you operate. And the type of results that we get once we do all this, we plot out on a graph for you, and this is a graph of distance from the point of release versus the radiation level. So for a pool fire, which was ignited after the pool had had a chance to develop, is going to generate this sort of plot. And you can see that on the left-hand side, you've got a flat area which is above the pool, where the radiation level is about constant, and it drops off considerably with distance from it, down to a distance of, in this case, 40 meters. It's quite a large pool fire, but you can see that it follows a sort of, would you say that exponential? It's like that. It's a nice curve anyway that goes down. For a jet fire, we have a similar sort of plot. Once you're downwind, the radiation level drops off. And again, you can see there that we've done this for two different weather conditions, a 1.5 F, so 1.5 meters per second wind velocity, stable conditions, and 3 meters per second velocity under less stable conditions. So you see that those weather conditions do indeed make a little bit of difference. And that difference could be significant, especially if there's somebody standing there. Now, judging whether you're going to do any harm or not requires some kind of measurement and thresholding. And we generally use 3 levels, 4.7 kilowatts per meter squared, 12.5 and 37.5, 37.5 being 100% lethal, and 12.5 being around 10% lethality as well. It gives people chance to get away, but it still wouldn't be very, very pleasant. And 4.7 is still causing, burning of skin and so on. So people would tend to escape from that quite quickly, but it doesn't take much more for it to become lethal. So it's worth understanding those numbers. For a flash fire, we've done a plot here, and you'll notice now that we are more omnidirectional. So this is a plan view of a flash fire envelope. We've got crosswind distances and downwind distances. So the plots that you see correspond to flammable limits. So, or percentages of flammable limits. I think we go down to a quarter of the flammable, 25% of the LEL. And that gives you the range over which you might expect to ignite your cloud if there were a source of ignition present. And vapor cloud explosions, and this time you'll notice that the y-axis is the overpressure in bar, as is calibrated there. So that's an overpressure plot. And once again, that starts off high, and as soon as the cloud runs out of fuel, it drops off reasonably quickly. It was one of the features of Buncefield that once the cloud ran out of fuel, the amount of damage that was inflicted was curtailed quite quickly. But anything within that high pressure range was thoroughly destroyed. The reason we have data like this is that we've done testing. Places like the HSL, the Health and Safety Laboratory, they will test explosives, and it's a power law relationship. So they'll set off a certain mass of TNT and then work out what the equivalent is based on the chemistry of the component that you're handling. The other way that we've got the data, for example, for the damage for buildings, is because we have very good data from the Second World War. When bombs were dropped on London, and so we got a very good idea of the amount of damage that a particular overpressure level could do. So for explosion damage, we have a similar sort of scale. We work here to 0.03 bar, 0.1 and 0.3 bar, and the effects on structures and the effects on people as well. It's generally speaking better for you to be outside in the event of an explosion, because it's things like the flying glass, collapsing of walls and buildings that produce an awful lot of the fatalities associated with explosions. And then toxic impact as well. And we have two things to consider with toxicity. One is the nature of the chemical and its mechanism on the human body, and that's its toxicity. And the other is the exposure duration, the amount of time that somebody might be exposed to it. And that, when it comes to consequence modelling, is absolutely critical. It's a function both of concentration and of duration as well. So for some chemicals, a high concentration for a short duration might give you the same as another chemical's low concentration for a much longer duration. And we have means of extrapolating that and working it out. But first of all, you would get an MSDS, a material safety data sheet, which will give you the limits, which are quotable limits. So things like the ERPG, which is the Emergency Response Planning Guidelines, IDLH, immediately dangerous to life and health, TLVs, threshold limit values, short-term exposure limits, and so on. Those are tied into concentrations and times. Now, I had some years ago, I was looking at the release from a single cylinder of carbon monoxide. And because the cylinder was, the scenario we were looking at was where it discharged in about 2 minutes. So these values were not much use to us. But you can use two other values. One is known as the SLOD, or the significant likelihood of death, and the other is the SLOT, or the specified level of toxicity. And those are tied into a dangerous toxic load. And that's the concentration at which, it's equivalent to LD50, the concentration at which 50% of test subjects exposed to that for the length of time would be expected to die as a result. So if you do that, it means you can tailor the concentration that would give you that dose to the time that people will be exposed to it. In my case, it was 2 minutes. If anybody was standing next to the cylinder for the full 2 minutes, what sort of dose would they get? And was it likely to cause them any harm as a result? And of course, the ERPG and the short-term exposure limit would not have been any help, but you can derive those figures from things like the SLOT and the SLOD. So I actually find those two measures considerably more useful than the ones that you find on an MSDS. So we've got an idea of what the consequences might be, and we've got some numbers that go with it. Now it's time to look at the risk side of things, the probability or the frequency with which we might get the release in the first place and have that harm occur. So the likelihood is the probability or the frequency of an event, and it's estimated as one of the my slides are out of order. Estimated as one of the event for which the calculated the consequence. Yes, that's right. That's fine. So it's the scenario for which we're calculating the consequences. For example, a 10mm hole in the pipeline. So we need to know how often we might get a 10mm hole in the pipeline. So the way we do this is to first of all conduct a parts count. So for each isolatable section, when we did our sectioning earlier, our sectionalization as it was awfully called, we look at the number of components, the number of valves, the number of pieces of fixed equipment, and we fill them in on a sheet. And then we attach that, or we compare that with a base frequency sheet. And that's available from various agencies. The UK HSE is quoted here, the OGP, which is, I've forgotten that particular abbreviation. No, it's going to escape my mind at the moment. But it includes the release frequency for various leak sizes and various pieces of equipment. I'll show you an example of what one of those looks like. So this would be a base frequency. So for things like compressors and centrifugal pumps and so on, we've got a variety of hole sizes and the frequencies associated with getting holes that size. Same for filters, flanges, heat exchangers, big launchers is in there as well. So those are the frequencies we might expect that kind of hole or that kind of release per year. And obviously, the more that you have of various items, the more likely it is because you've got multiple opportunities for it to happen. So we tie it into a sheet like that, and we produce our own sheet, which might look like this. So we'd look at the inline equipment, we'd see how many pipe runs we got of a particular diameter, compare that with the base sheet, And that's going to give us a factor to multiply by that base frequency, which gives us an overall frequency for the section plant that we're looking at. We would do normally a range of leak sizes as well. Now, bear in mind that a smaller leak size is going to have a lesser consequence than a larger leak size, unless you don't notice it. A 2 mil hole might go unnoticed for a while, whereas a pipeline rupture you might notice quite quickly. So be careful when comparing apples with apples, as they say. But we would do a range normally: a small, a medium, and a large hole, and some ranges there, and also a full bore rupture. And this is fairly standard, and those of you who come from coma sites will be very familiar with that kind of approach. There is also a database provided by other agencies. So I mentioned the UK's HSE database. DMV has its own database, the Centre for Chemical Process Safety, the CCPS. The TNO, the Netherlands organisation, it used to be called their Purple Book, I think, but I've slept since then. They've updated it. It's now called the BEVI 3.2 guidance. Cox et al., the Cox leads loss prevention in the process industries as well, which will give you some frequency data as well. Now, a word of warning on this as well. If you use database values, bear in mind that those database values will have come from all possible corners of the earth, under all possible maintenance regimes and qualities of company, shall we say. If your maintenance program is lacking, leaves a bit to be desired, maybe you haven't done any for a while, your frequencies might be worse than the ones quoted in the database. So be careful. Make a realistic and qualify where you actually use these figures to make sure that you're not claiming credit where it's perhaps not due. But what this allows us to do is to come up with initiating event frequencies, a structured and thorough or more robust way. So we get a genuine idea of how likely it is that for that year, we're going to get a 5 mil hole in a particular piece of plant. That would give us the likelihood of getting the release in the first place, but we also need to look at what the likelihood is of getting a particular consequence as a result. So I go back now to where we had our releases and the event tree that went with it. So if we had a flammable liquid released, as is shown on the diagram there, and the operator controls it, we get a minor in-house incident. Somebody gets told off. But if he doesn't control it, we might ignite it and we might not. If we don't ignite it, we have a loss of containment, a reportable incident. But if we do ignite it, we've got potential for pool fires, vapor cloud explosions, etc., and therefore we might hurt somebody. So we can now apply likelihoods or probabilities to those as well. And again, this will very much depend on the way you operate, as to whether you think you've got your source of ignition under control, the particular material properties, is it likely to self-ignite like hydrogen will, whether you've got an operator who is nearby in order to do some control, whether your control system is going to report the relevant data quickly enough to him to enable him to effect an action, and so on. So you can choose then the likelihood of the yes and no answers to each of these to fit your own circumstances and come up with a likely consequence as a result, or the most likely consequence as a result. So therefore, we need to consider all these things. The frequency, we look at that through the base frequency and the databases that we looked at. Your plant itself, the number, the inventory of equipment, of the fittings that you've got, so your parts list. Where there is automation, to isolate, which means you've got a fixed inventory at a known pressure and temperature, so you know what's escaping. The probability of ignition is going to depend very much on the size of release, the material properties, and the way you operate. The weather, the wind direction, what time of day it is, and of course whether that is going to hurt people. So the number of people and the probability that they are local or at least local or within the cloud or within the radiation envelope in order for them to be hurt as well, and therefore the probability of fatality. That ties us right back into that acronym that I introduced at the beginning, the LSIR, sorry, the abbreviation, and the PPL, probability of a fatality, and the location-specific individual risk, how likely it is that we hurt somebody as a result of all this. And that's where we come into the risk summation and the analysis, looking at how we use these figures in order to make people safer. So we have two measures. One is individual risk and the other is societal risk. Individual risk is the risk experienced by this hypothetical person at a particular location. So it doesn't have to be the same person. If somebody is on plant at a particular location, he's relieved by somebody else, they count as this single hypothetical person because it's the location and the consequence that is important. It's not whether we hurt Joe, it's whether we hurt anybody at that location. So this gives us these two measures, the location-specific risk and the individual-specific risk. And that's expressed per year. So that then allows us to tie in to a tolerability criteria, how often we are prepared. That sounds bad now, doesn't it? How often are we prepared to kill people? We should be never. But how often does it have to happen before we get prosecuted and we find ourselves in serious trouble? And then individual risk controls, which is it's a commonly used presentation to inform public. It's mainly used for land use planning, actually. And that represents a contour which represents the frequency at which any person who is assumed to be there permanently sustains a given level of harm. So it's a frequency plot. So typically in land use planning, we use a 3-zone plot, and these are calibrated to a risk or a fatality risk of 50%. So 50% risk of fatality at a rate of 1 times 10 to the minus 5, 1 times 10 to the minus 6, and 3 times 10 to the minus 7. So that's 1 in 100,000, 1 in a million, and 3 times 10 to the minus 7, whatever that, 3 in 10 million. But that's a 50% risk. So you can plot those on a map, and therefore determine the number of people who might be hurt from a societal point of view from a single event. And these are the kind of plots that you'll find. Ours are much nicer because they're done on ordnance survey maps, but this is a sort of a more stylized version. But you can see there that in the innermost circle, we've got 10 to the minus 3. So there would be a risk, or a 50% risk of fatality of 10 to the minus 3, a 1 in 1,000 year event that anybody who'd set up camp permanently on that blue contour would suffer that level of harm. So the question is, what is acceptable and what isn't acceptable? And I appreciate that nothing should be acceptable, but we live in the real world where there is no such thing as zero risk. So we have this to help us, and this is known as the tolerability of risk carrot, usually because it's orange, but we've divided this into red, yellow, and green. At the top, we have the highest risk activities. At the bottom, we have the lowest risk. And therefore, if you do the calculation, you find that the individual risk for a worker is greater than, for a single fatality to this worker is greater than 10 to the minus 3 or 1 in 1,000, you are operating in the intolerable region. And therefore, you must stop work and put in place some risk reduction measures in order to reduce that risk. First of all, to the yellow region, and then ultimately to the green region if you can reach it. The risk there is defined for a single fatality at 10 to the minus 6 or 1 in a million. So there's only 3 orders of magnitude between them. So this is why quantitative risk assessment trumps semi-quantitative risk assessment, because when you're doing it semi-quantitatively, you are working in orders of magnitude. And if there's only 3 between the red region and the green region, you can find yourself arguing yourself into the intolerable or into the broadly acceptable region very easily. So doing it with quantitative risk assessment gives you much more confidence that you've got a much better realistic understanding of what the risks actually are and where you need to take action if they are too high. This diagram, incidentally, you can get from the R2P2, or Reducing Risks Protecting People document from the UK's HSE. It's on free download, and it will tell you how this was derived. It was derived from various studies that were conducted over the years, and looking at various occupations and so on as to what was an acceptable individual risk of fatality per annum. We do something similar for group risk or societal risk, and this is really the risk of harming a large number of people from a single event, and we do it by using something called an FN curve, a frequency number curve, and they look like this. You have a cumulative frequency going up here from all events and a cumulative number of fatalities going along here. And the idea is that we've got three zones again. We have an intolerable region up at the top, a broadly acceptable region at the bottom, or negligible as is labelled here, and the tricky bit in the middle, which is known as the LARP region. LARP stands for as low as reasonably practicable. And if you find that your risk either from an individual, i.e. the yellow bit here, or from societal risk is in the LARP, you need to do two things. Well, you need to ask yourselves two questions. This is in the guidance, these questions. They say, what more can we do to reduce the risk, and why haven't we done it? And the answer to why haven't we done it is usually it's too expensive. So some form of cost-benefit analysis must be done. So you must demonstrate that the costs of any remedial work are grossly disproportionate to the level of risk reduction that they would introduce. Otherwise, you are not a LARP, and that you should put in place some risk reduction measures. So that's what a LARP means. Now, this diagram is also calibrated, and the calibration point for this is 50 fatalities at a rate of 1 every 5,000 years, which puts this red line, I don't know if you can see my mouse moving, but I've got it on 1 every 5,000 years and 50 fatalities, which gives me a point, and then you run the lines through it, and everybody's does the same. It has a sort of severe drop-off style of the plot. Everybody's looks the same, really, but it does exactly the same job. There is an intolerable region, a broadly acceptable region, and a region where you need to make sure that your risks are as low as reasonably practicable. So because QRA is better than the carrot that I showed you, the upside down triangle, it allows you to make much better, more cost-effective decisions and be more targeted in your response when it comes to putting in place additional measures, which are going to be the recommendations that fall out of any QRA. Where you do get recommendations, view them with a certain amount of intelligence, I would say. For example, recommendations for QRA might be something of this sort: hazard elimination. Can you use something less harmful? Can you put in place some additional safety measures, i.e. spend a bit of money, go out and buy something that reduces the frequency or reduces the consequence? After the event, can you put in place some mitigation measures, blast walls, deluge systems, emergency response systems? Or could you do something like moving people out of the way, which is often the most cost-effective solution and covers you through a whole range of potential losses of containment. If you had 37 potential jet fires that could hurt 15 people, if we can move those people away, you don't have to look at the individual 30 jet fires anymore. So look at, when you get the report from anybody who's produced it for you, and you get the recommendations, look at them individually, certainly, but look at them in the round as well. They may find that there are better solutions that can be made that would cover you for a number of potential scenarios rather than just individually looking at one scenario at a time. It may save you a little bit of money. But that's essentially what you have to do. The QRA bit, the frequency analysis, the consequence analysis, the numbers that sit behind you, trade off conservatism for accuracy. That means you can spend your money better. That means that when you do spend your money, you'll get better value for it. And that means you can do more good with it as well, if you see what I mean. That means you're doing people more, helping to hurt people less as a result. So I do hope that's been at least interesting and helpful. It's the kind of thing that we do, we get asked for occasionally. So if you think it's something that we can help you with, please do get in contact with us. But otherwise, it's just coming up to the hour, so I've not done too badly. But thank you very much for your attention, and enjoy the rest of your day. Goodbye for now.